lecture recitation video, we are going to go over some double integrals. First of all, let's cover, we have a definite integral for a function with a single variable has, where the value of x lies between and a is less than b. So this is applicable for a one-dimensional space. But what about the two-dimensional spaces or higher dimensions? So in this case, let us assume a region R square, which is a rectangle between the limits a, b, and c, d. According to Fubini's theorem, if fxy is a continuous function on R between the limits a, b, and c, d, then area is given as or it can also be written as the thing which we need to consider is the inner differential, that is CD uh, dy matches with its inner limits, that is c and d, and the same applies with the outer differential and limits, that is dx and ab. So to give you as an example, let us consider like this is what it's generally given as. So we need to make sure that our outer and inner differentials to match, or it can also be dy. So in the first case, when we are considering the inner limits c and d, f of x dy, we can hold x as a constant and integrate the entire function with respect to y. Or in the second case, we can hold y as a constant and integrate it with respect to x. Let us compute some examples. Um, Consider this function given to us as with the limits and so this is given as the outer limits 2 4, inner limits 1 2, for the inner limits dy and the outer limits dx. So let's solve this. 2 4, let's consider the inner function. 4. So here we're going to keep x as a constant, so we're only integrating y between the limits 1 and 2. The entire thing still lies between x. 4, this becomes 2xy cubed, 1 and 2. Fourteen x dx. Now let's integrate it with respect to x. Then it becomes square by 2, 2 and 4. That is 7x square between 2 and 4. That's 4 square 16 minus 4, that is 84. Another thing I want to focus over here is, even if we change the order of operations, or like if we change the inner limits and inner operand with the outer limits and the outer integrand, the result should be equal. So let's try that method as well. So we're given the right, this is our I square. So this can, initially we took our inner limit as 1 2, let's take it as outer limit, and 6xy square with dx and dy. Pay attention, we have interchanged our outer limits and the inner limits, but the combination of limits and its respect to operand remains the same. So now if we solve this, so here we need to keep y as a constant, so it becomes 6x is x by 2, between 2 and 4, the entire thing lies dy 1 and 2. So 3y square 16 minus 4, that is 36y square. So differentiate, integrating between with respect to y, 84. Therefore says and dy. So in this way we can solve the double integral. Okay, let us consider another example. Uh, we have a function x e power xy and the a, where the limits are given between -1 and 2, and 0 and 1. In this, we can solve this by substitution, and in this, like, we can see the methods of substitution and also how the two limits are being used to solve this entire equation. So this becomes 2 0 to 1 c power xy of dy and dx. So but let's first consider the inner term, that is 0 to 1 and dy. So here we keep x as a constant and we only integrate it with respect to y. So let us take xy as u, differentiating it both sides. Then this becomes then this becomes e power u, x dy is, so the integral of e power u, e power x is e power x per u between 0 to 1. Change it back to xy. This becomes, now let's integrate it with respect to x, and this becomes e power x minus x, that is between minus 1 and 2. So e power 2 minus e power minus 1 minus 2 plus 1 3. This is what we have. And it, in a similar way, as explained above, even if we change the inner and the outer ones, the resulting output integral should be same. And also one of the thing I want to suggest to you is, so sometimes the order, or whenever we are given a set of limits, inner limits and the outer limits with respect to the integrand, uh, by looking at it, we can try to find out or try to arrange the equation in such a way that when we solve, it's easier with the limits. So if we find a bigger set of limits, let's keep it to the end and first try to solve it with the smaller ones, so that try to make it as easy as possible, so that our, when we expand it, or like when once it gets into the integral part, it shouldn't become a difficult task for us. I mean, we can still solve it, but always try to choose it in an order where it's easy to solve. And another important note I want to add is, let us consider if we have a two-dimensional function which is a product of two functions such as g of x and h of y. Then, and if we are integrating it over the limits, then this becomes h of y dA. This can also be written as AV h of y. So let us see how this works. Let us take an example. Let us consider this function x cos square y of the, with the limits minus 2 and 3 cross 0 and pi by term. So this, applying the above formula to it to see whether it still holds. So here we have g of x is x and g of square y. So we can write this in the format of Okay, so and let's simplify cos square y has 1 minus cos 2y, so 1 plus cos 2y by 2 dy. So solving this, we get x is x square by 2 between minus 2 and 3 multiplied 1 by 12 y plus sine 2y by 2. This is between 0 to pi by 2. 3 square minus minus by 2, and then we have 3 square 9 minus 4 5 by 2 times by 2 and 5 by 2. That becomes 5 by times 8. Another method to solve, if we can break up the function only of like x times a function of only and y, we can do it as a two integrals individually and multiply the product together. So I hope this helps, and thank you.